If you work with Linux systems, you've probably heard of the terms hardlinking, softlinking, and maybe reflinking, depending on your file system. But what exactly is the difference between a hard link, a soft link, and a reflink? And which should you use? In this video, let's quickly explore this topic. So first, you need to understand that there are two essentially views to the file system. First, you have the logical or the software view. And then on the other hand, you have the hardware view. So from the perspective of the hardware, you have a physical, let's say a hard disk drive, could be an SSD, could be anything. You know, if you have a hard disk drive, you've got your platters, and you'll have like your read-write heads. But essentially, you're going to be working with these physical sectors. So for the uninitiated, if you have multiple platters, so this is your top platter, you have sectors. Files are written to and read to in the in each sector. You also have cylinders, which is basically, well, if you look at this like three-dimensionally, a cylinder will be the three-dimensional area that you're in. And you also have your appropriate rings. We don't need to worry about whether you're working with a hard disk drive or whatever. Let's just say that when you make a file, your file is going to get stored as a block. So let's say I make a file. Say, for example, I have a file called hello. And I'm not going to talk about the fact that on modern file systems, the metadata for the title and stuff is stored separately in the file. Let's just assume that you're using a very simple file system and the title of the file or whatever is the same as the content. So that's going to be saved in this block, right? So my file system is essentially a pointer to here. When a program says, let's say this is block like 100 or something. So when I have a program and the program makes a system call and that program wants to open this file, well, what the file system is going to do is it's going to take this and say, oh, hey, yes, I know where that is. That's going to be at block 100. And so it's going to tell the software, okay, all right, I want you to go and look up and read from this actual hardware address. And of course, you'll have the driver that can talk, whether it be AHCI or NVMe. You'll have that, and then here you'll have your file system. So the file system will convert that, and then you'll have your drivers to talk with the appropriate hardware. But that's besides the point. Essentially, you make a software call, and it's going to read here. Now, of course, this gets a lot better. If I only had, say, I have a second file, and this one was hello world, and this file is stored somewhere else. Maybe it's a smaller file. It's going to be stored in another block. Say this is on block 150 or something, right? And essentially, it's a pointer to here. So now when a program wants to open the hello file, it's going to go and read from this location hardware. And if a program wants to open the world file, it's going to go and read from this location and hardware. So far, so good. But if all my file system had was just files with names and pointers, it wouldn't be a particularly useful file system. So most file systems use a hierarchy. So for example, let's say I'm in /home/Tony, right? So let's assume that's our root directory. Now in here, I can have documents, and my document can have our foo, our bar, and I can also have music. So each of these is going to have a corresponding thing. Each file will be written somewhere on the hard drive or solid state drive, whatever. I'm not talking about the metadata where folder names and this hierarchy is stored. I think for the intents of this video, you just need to know that they are stored. Maybe in a different video, I'll talk about ButterFS versus ext4 versus XFS, FAT32, NTFS. If this was something like FAT32, just assume that all of these are stored in some chunks at the front of the drive. But anyway, we have these blocks for the actual files. So my file foo is actually going here. Bar is actually here on the drive. Maybe my monstercat MP3 is here. Something like Tristram and Brocken. And my Linux audio WebM file is going to be here. My apologies for constantly moving this piece of paper. This is what I was supposed to be writing on the glass, but then I realized that dry erase markers don't work too well on that, and it's going to permanently stain my old screen's backlight panel that I'm using to light this. So we have we can have any number of folders, and typically, most file systems are implemented kind of like a tree. So, if you're watching this video, you've probably heard of the typical Unix file system, right? You'll have slash as the root, slash etc for config files, slash home, slash user for user space files, slash bin for binaries, var for variable data, mail, web servers, so on and so forth. Slash lib. You've probably heard of the Unix files hierarchy. There are many videos that discuss that in great detail that I would recommend. But so essentially, now I open my Linux audio file. We're going to read from, say, this is like block 1000, 1500, 2000, and say, like that's bigger. So say this is like 8000, these are all made up numbers. These normally sectors would be like 512 or 520 bytes. 512 with the exception of some enterprise drives, which have additional space for CRC checksums. Anyway, that's beyond the scope of this video. We have our where they actually are in the hardware. So programs will go look this up. Now, yes, I said this video is about Hardlinks, Softlinks, and Reflinks. I'll get to that. So this part hopefully makes sense. Next, let's talk about linking. So the first type of linking is a hard link. It changes the nice pretty tree of our file system into a graph. So first, let's talk about hard linking. So let's say I wanted to link bar and foo. So say I no longer want this bar file, right? Instead, I want this bar file. I wanted bar to actually point to foo. So I don't want to treat these as two different files. I want them to essentially be the same thing. So I want to be able to open either foo or bar, and it'll do the same thing, and they'll be synchronized. So that's a hard link. So the way you would hard link is ln, and then the source of the link, so in this case foo, and then the file you want to link to, bar. So this is the original, and this is basically the copy. And I guess assume that the file does not exist, because that's going to create the file. What a hard link will do when you run this, when you run ln foo bar, it's going to create a new file called bar. Well, it's going to create the metadata for it. But unlike these other files, which got their own hardware locations, bar is actually going to go to the same block, to the same address as foo. So essentially, we have two different files in the logical side, but on the hardware side, there's only one file, and both of these just point to that one file. What does this mean? I open file foo, I'm reading from block 1000, so say it had the words hello world in it. I open bar. What happens? Well, bar is not its own block. It's also pointing to the same block as foo. So when I open bar, I'm going to open the same block. So what am I going to read? It's also going to say hello world. Now, what if I change this? Say I put flurble into the file, right? So I open bar and I write the word flurble. And then I save this file. What happens? Well, this word is going to get written to this block. So I can close the file and then, it's in this block. Then say, what happens if I go back and I open foo? Will foo say hello world? No, it'll say flurble because this file has essentially overwritten what's in this block with the word flurble. So it's no longer hello world, it's now this new word. So when you go to open foo, it'll be the same thing. Now, I think you can see why hard links can be slightly risky. If you hard link these files and I update this file, this one also changes. Now, there are a couple caveats, let's say. So let's talk a bit about how so most applications will unknowingly follow hard links. And by the way, these two files, they don't have to be in the same folder. I could have linked this file called Linux audio to foo, and it would have done the same thing. Basically, instead of Linux audio going to this block, it would have come to this file. So you can link any hard link, basically any file to any file. You don't have to, it doesn't have to be in the same directory, doesn't have to be all that stuff. You can link across folders, whatever you want. tar, for example, is smart. If tar sees hard linked files, it will only put it to the archive once. It'll put the name of the second one, but it will not rewrite the data, so it won't waste that space. Some applications are smart. Some applications will basically unknowingly follow hardlinks because according to the application, there's nothing special about this. It looks exactly the same as a normal file, and when it opens it, it just goes here. So there's nothing special or blue about this, actually. I just did that as a demonstration. It'll look exactly like a normal file to an unknowing application that doesn't like make the system call to check. Let's talk about caveat number 1. What happens if I go and I delete foo? Uh-oh. Now that's gone. What happens? So that means this arrow is going away. Now this file block, if you recall, was originally created for the file foo. So when I delete foo, you might expect that this block will get deallocated. It'll get marked as free on the hard drive. So what happens to bar? Well, actually, nothing. The way hardlinks work is as long as there is at least one file pointing to this block will remain allocated. So I had a file F, I had a file B. Originally F was this, B is hardlinked to F. And I delete the original file. Don't worry, the data is still here. This will not get deleted. When does this get deleted? Say I also delete the file bar. When that's done, so that removes this arrow here. Now, no files point to this block. So what's going to happen? Well, since nothing needs it, now this block can get freed. And it'll be deleted. So that's how deletions work. It'll wait for both to be deleted before deleting the full file. How do I unlink this? Now, I don't want bar to be a copy of foo. Now I want to be able to do something with it. How can I unlink this? Well, easy. Just like how we linked it using the command ln foo space bar, we can unlink it. So the command to unlink is called, wait for it, unlink. So I would do unlink bar. And what that will do is it'll remove this pointer and the bar hard link will be gone. So that's how you can unlink these to get them back into a normal file system. Let's see. Let's talk about, now let's say that I wanted to make my, I wanted to make a new folder here called text files. Let's say I made a folder here called secret. And in it, I wanted to put some text folder called text. And in here, I wanted my foo and my bar. Right? So what I want is basically, you say you wanted to make this text folder actually secretly just go to the documents, right? So say you wanted to automatically make everything in here get hard linked. Now, as you might imagine, you actually cannot do this. You cannot hard link folders. And I mean, let's talk about why. I want my text folder here to point to this. Well, what you'll notice is the way this is working, the way hard links work is it'll take the logical file and make it point to the same block in hardware. But as you know this, there is no, for example, if folders were being saved in these blocks, so say this was a folder at like 500 or something, then, this was a folder at, 3000. If this is not how it works, if it were like this, then one might think, well, instead of this pointing here, why can't we do what the hard linking did on files? Why can't we just get rid of that? And why can't we make this point here? And that's because these blocks don't exist. Folders don't exist in the hardware view. This is, in principle, why you cannot hard link folders, because there's no block for them to link. Instead, you can make a folder and you can hard link two items. I can do ln documents /foo secret /text /foo. And then I can do the same for bar. I can do ln docs /bar secret text /bar. This will work. This is valid. I can do this. You can link each file, multiple files that are in a folder. There's nothing wrong with that. You just cannot hard link folders or directories. I think every time I say folder, a little part of Randy dies. Next up, let's talk about Symlinks. Now, Symlinks are a little bit different. So let's use the same file structure. And now, let's say that I have a file foo. I really wish these pens were non-toxic. That's kind of concerning. All right. So I have foo. And say I want to create a symlink this time. So I want the file bar. And I want it to do, well, let me just show you what symlinks do. So option 2 is a symlink, which is short. I keep calling it a symlink, but it's actually short for a symbolic link. So the way that one you can do that is you do ln-s. S is for symbolic. Foo bar. So that will create a new file called bar. Now symlinks are different. Symlinks are not transparent. So applications will be able to see that they are symlinks. Now, for my Windows users might be quite accustomed to symlinks actually, because they're simply just links. So file foo goes to this file, as we expect. Now, what happens when I symlink this? Well, instead of what a hard link did, which was that it kept the file hierarchy just like you would expect, and it basically made both of them point here. A symlink makes this point to this file. This is why they're commonly called shortcuts or symbolic links, because they're not separate links that go from this side to here. A link, as in a hard link, crosses this bridge from this logical side over to this hardware side. A symbolic link does not. A symbolic link stays within this logical pipe. It stays with these symbols where, you can think of each file as a symbol. So it actually just, so when an application opens foo, it'll go here as expected. When an application tries to open bar, it will basically get redirected to the file foo, which will then open this. The end result for an unknowing application is the same. But applications must be willing to follow symlinks. So think of it this way. If I have a website, and in my website, I made like a DNS record with a CNAME, right? So, which is like a hard link. So when I go to a part of my website, completely unknowingly, or, it's the same. It's a different link, but, you can make it go somewhere else. This is like a 301 or 302 redirect. Like someone tries to open bar, and they know that they're going to get they know they're getting redirected from bar into foo, and then they can open foo. So like when you open this, it's like, oh, hey, I'm not actually a file. I don't exist on this side. I am only a link on the software side. I'm a shortcut to tell you that you should open foo, and you can open foo to get the file. So this is very common again on Windows. This is just called shortcuts because, well, you might have heard of your applications, right? You create shortcuts on your desktop, for example. What is that? What is that shortcut on your desktop? Well, it's just a symbolic link. When I try to open, Microsoft Word on my desktop, it's actually going to go to Program Files / Microsoft Office / Word, and then it's actually going to open that binary. So these are symbolic links. Now, why might you want to do a symbolic link over a hard link? Hard links are good if you want it to be transparent to the end application. Symlinks are good if you want the end application to kind of know that there's a link. And they have one other advantage. Remember how I said that folders cannot be hard linked? And that's because folders don't have a corresponding block on the other side that you could create a symbolic link to. You can symlink folders. So I say I had this folder text. And when I want a text to contain foo and bar, basically. So I don't want to link these files. I just want the text folder to go to documents. Well, I can symlink an entire folder. And unlike the hard link, because it's purely on the software side, this is a link I can create. So what that will do is the OS will go, oh, you want this to just go to here. Boop. And it will happily create that symbolic link. So now when I go to my operating system and I try to ls this file, this will actually just, we'll see the foo and we'll see the bar. But if I were to type ls, the operating system, and I say I was in the secret folder, right? And I type, say I'm here and I type ls secret, or let's say I type ll, which is usually symlinked to ls-l, or I can do la. So, right, I do this on the folder secret. What do I get? Well, it'll give me the okay. It's like, okay, so, you have d whatever, rwx, rx, rx, for example. And then the size. Ow, my hand is getting cut by my LED strip. All right. And it'll then say the folder, you have the folder text, the directory. But text is actually a symlink to documents. Now, if you're symlinking folders, there are a couple things you need to be aware of. You can create symlinks using relative addresses. You can create symlinks using absolute or complete paths. So for example, /home, /Tony, /secret, /text. So say I wanted to link text over to documents. What I would do is I would go ln-s /home/Tony/documents space /home/Tony/secret/text. And that would link this folder. Now, one thing that you want to be cautious of is you can create invalid symbolic links. So if you're creating links using only relative links, it is something that you should keep it. So say I'm doing ln, and I say I'm in secret, I do ln-s ... documents, and then like text or dot. Whenever you're using relative addresses, there are certain combinations that will work and certain combinations that will not work. And same with absolute, it's something you'll want to keep in mind because it will affect how you can open the symlink. You may or may not run into this issue. You will probably be fine, but it is something I'm pointing out so I think that's an overview of symlinks. So symlinks are basically, just a quick recap, there are shortcuts that are on the logical side, so you can link a file to another file. So when you go to open this file, it'll say, hey, I'm actually a symlink. Do you want to follow me? And if you follow it, you'll go to this file and you can open it to the hardware. Unlike Hardlinks, this is not a transparent process. Applications will be able to know that something is a symlink, and they'll usually have the option about whether or not they want to follow said symlink. You can also symlink directories because you can hardlink them because there's nothing on the hardware side, but you can't symlink them purely here. And you can see what I mean by this changes the tree into a graph. Because now I can have files that go up, that go down, that go all around my Unix file system. So finally, let's talk a bit about reflinks. Reflinks are special because they're a bit different than how the other links work. So reflinks are actually copy on write, essentially copies that get made of files. Now, reflinks are not universally supported. So hardlinks and symlinks you can do on pretty much any file system. Reflinks work on Btrfs, ZFS, and I believe XFS. I don't think it works on ext4. If it does, someone please correct me in the comments and I'll put an errata in the description here, or an update. So what are reflinks? Well, what is copy on write? It's kind of what it sounds like, but let's discuss it. So let's say I wanted to, again, copy foo and bar to here. So we can reflink the directory, or we can reflink the files. So let's say I reflinked it. So a reflink starts its life pretty similar to how a hard link would. And you can reflink by doing cp, the normal copy, -- reflink source destination. Let's start with our simple example. Let's say I want to reflink foo and bar, right? So what's going to happen? Well, the reflink starts its life similar to how a hard link would. So it's going to start by pointing here. However, File systems like ButterFS, CFS, and XFS are a lot smarter. So yes, this is going to point here, but they're going to keep a star. And the star is that this is like a read only. What does that mean? Well, it means that, well, if I copied foo to bar with a reflink, bar doesn't take up any more disk space right now. Because if you try opening bar, you're just going to open the same block here. So bar doesn't take up, other than the metadata, which is a couple bytes or kilobytes, bar doesn't really take up space on the hard drive, which is great. That's one advantage of doing reflinks. It's great for deduplication. Now, I said that in Hardlinks, say this file originally contained the word hello. And I open foo with vim, I write hello, and I quit. Then I open it with bar. What will the file say? Well, it will contain the word hello. Because this wrote to here, and now I'm reading from here. It's the same thing. But let's say I then change this. And I change this to the word flurble. What happens? If this was a hard link, it would just write here, and then it would all get replaced. But the file system has kept track of this special pointer here, and it knows that it should only ever read from here. But we just did a write. We changed the content of this. So what happens? The file system goes, uh-oh, you changed something, and this was a reference. So what it's going to do is it's going to say, all right, you wrote that, so now it's time for you to no longer point here. So this will keep the word. Let me write the word in the box. So this file had the word hello. And foo will keep pointing here. But we updated bar. We opened bar, which was the same thing, and we wrote flurble. So the file system goes, uh-oh, all right, let's make a copy of it. And it'll take the word flurble and save it as a separate file and give it like a new address, right? So now these files are actually basically no longer linked. If you open foo, it'll say the word hello. If you open the word bar, it'll say flurble. This is great because ButterFS uses copyright write functionality in numerous places within the file system. For example, one of the best features of ButterFS is that it allows for snapshots. A snapshot is kind of like a backup. I mean, that's what it sounds like. It's basically you save the file system at that point. And usually you can make it like a snapshots folder. You can snapshot this and save it. And it takes no additional disk space because it's copy on write. As long as you don't touch any file, it will not use any additional disk space, save for the metadata. But, you know, you go and you start updating your documents, then the file system will copy everything and then it'll start using space. So as we saw here, when bar was originally reflinked, it took no additional space, but when we opened it and we made a change, then it get copied. And this is why it is called COW, which stands for copy on write. Because think about it. Normally when you would do a copy operation, the file system would immediately read all the bits here and write them to a new block with a new address and would point it here. Like if I did a normal copy of this file, that's what would happen. You would immediately get the, what would happen is, let's draw that and then it'll maybe make more sense. So I copy this into the file bar. So I do cp foo bar. The OS will happily copy this file for us, give it a new address, and it'll basically live here. But, you know, so this is normal copy. But what copy on write does, as you saw, is, I mean, it's as the name suggests. When you do the read operation, it will not make a copy. So as long as I'm only doing reads, I'm going to keep reading this block. But the first write I try to do, say I try to add a new line, or I try to edit the word to be flurble, or baz, bath, nord, whatever. The moment I try to update that word, that's when the copy takes place. And this is why maybe it shouldn't be called a link, but it's a link until you make a change. And when you make a change, copy on write kicks in. And as Alexa says, when we wrote something, so say we changed hello to bienvenue, then it'll get copied. So copy it on the write operation with a new address. It starts as a link at first. When you make a change, then when you do a write, it'll get copied. So advantages and disadvantages. If you had done a hard link, say if you want the two versions to always be kept in sync, that's the job of a hard link. Then so that when you update one, the other will implicitly basically get updated because they point to the same thing. But if you want to do this, maybe like a backup, maybe like something, you'll have two files, you copy it, and you don't really want it to take up disk space. You just want to have this like snapshot or copy of it. And then if you do make a change on purpose or accidentally, that copy will get updated. It'll get written and updated. And then, the rest is basically a traditional copy. So what this means is that I can copy a 2 terabyte folder in a matter of seconds because it actually doesn't get copied as long as it's on the same hard drive. If it's on different drives, it will get copied. So say I do cp reflink documents text. So this is going to recursively go. It's going to create these items here, but they don't exist yet. They're going to point here. So the copy operation, really, really quick. So let's say these weren't text. Say these were like big videos, right? Say it was like my Linux audio thing, and it was a big video. Right now, these take up no space. And yeah, so you can, by the way, of course, you can CP folders, and if you, provided that you do CP -R for copy recursively, because folders are basically like a normal copy operation will only copy the files in folder. If you wanted to actually descend and open each directory and copy the contents of that directory over, you need to give it the -R so it will recursively go through it. But anyway, these point here, and then I update bar, say it said world, and now we're going to make it say planet. Then it gets copied here, and then we get a new block allocated for it. And so that's how reflinking works. Reflinking is great. Reflinking is particularly good if you want to deduplicate items, because I don't want to say there's no downside to it, but if you have two copies of the same file, unless you're doing it for a bad reason. So what's a bad reason? So you've made two copies as a backup or to protect against bit rot. Well, really your solution should have been creating parity files. And you can either do that with a tool like Part2, or you can ButterFS and ZFS natively keep multiple copies of a file. And on ZFS, you can actually tell the drive, I want you to make duplicates of this file, because and then, it'll basically be like a RAID 1, but on the same disk. So if one of the two copies gets corrupted, you don't lose the data. Of course, the downside is if the hard drive dies, you lose both the copies. So it's not as good as something like RAID Z1, which is the ZFS version of RAID 5, basically. And RAID Z2 is basically RAID 6, but that's a separate discussion. Anyway, so yeah, that's how it works. And you can easily use a tool like rmlint. We'll go through your files and clean it up. I think this is as opposed to a tool like dupe remove. What a tool like dupe remove will do is dupe remove will look at the extents of the file. So what is an extent? Well, this file isn't stored as one block. Each file is made up of extents on a file system. And so technically, there isn't one pointer here. In short, this file is split into extent 1, extent 2, so on and so forth. And each of these point to these blocks. Well, they actually point to multiple blocks, chunks that the file system will break up into, and each of those chunks can go in a different place. So dupe remove will actually check the extents. So if these files had the same, say, first paragraph, it can actually go and it will go through here and say like, oh, hey, extent 1 of this file. Because say you started with like lorem ipsum, lorem, whatever. It'll go like, oh, this extent is actually the same as the first chunk of this file. So it'll actually go and like link you to the extent level. Now, of course, the smaller you make your extents, the more metadata you add. So at some point, if you make your extents too small, yes, you might match more chunks and essentially deduplicate them, but also you added a ton of metadata because each of these extents needs to have its own metadata saved. But anyways, that is hardlinks versus reflinks versus Softlinks, and a bit of couple notes on copyright right and dupe remove. I hope you enjoyed this video. I think this is a time where I then say, thank you so much for watching this video on Hardlinks versus Reflinks versus Symlinks. I hope you enjoyed it. I hope you learned something. I hope you learned something new, or maybe it strengthened your knowledge on Linux and why people like to talk about file systems like ButterFS and XFS and ZFS and copy and write functionality. I hope it's give you some detail into why you might want to use a hard link versus a soft link. With that said, thank you all so much for watching. If you found this useful and you'd like to see more videos like this or about whatever other random projects I come up to, consider leaving a like on this video and subscribing to my channel. Helps me out a lot. Have a great day, and I will see you next time. Bye.